So the next question we're going to look at, how many 4-digit numbers can be made from the digits 1, 2, 3, 5 with no repeats? What that means is you can't use one of those numbers more than once, so that the number we get is divisible by 5. Then what is the probability a random arrangement of 1, 2, 3, 4, 5 is divisible by 5? I can see a hand up, but actually I'm going to strongly push you down one route. In any question like this, you saw it a bit before, put down 4 markers. I think this is a really good way of doing some of these questions, particularly when they get hard. What do you know about the answer if it's got to be divisible by 5? It's got to have a 5 there. Okay? How many ways are there then of filling that position?
1.
This position here. Yeah, just one way. Okay? One way of filling that position. These 3 over here can be any of 1, 2 and 3. So they can be arranged in
3
factorial ways. So to get your answer, you times these together. So 3 factorial
6
times by 1 is, 6. Okay? There are 6 ways of arranging it so it ends in a 5. It's divisible by 5. That's like part A of the question. Part B of the question said if we had a random arrangement of any of the ones we could have from 1, 2, 3 and 5, what's the probability it will be divisible by 5? So a probability, we are looking for a fraction with 2 numbers in it. What can you tell me straight away?
What's the number? It's the number with no restriction.
I was actually going to... Yeah, okay, but I wasn't expecting that. Go on. Yeah, the top number, the one with restrictions, is what goes at the top. Okay, so that one there, the top number, is the restricted number. And the bottom number is the... Yes, the unrestricted number.
4.
Because there are... Yes, 4 factorial, yeah. There are 4 digits, so 4 factorial. Can we remember what 4 factorial is yet?
24.
24. 6 over 24 becomes, 1/4. Right, there we go for that one.
That's a lot easier.
Yeah, the answer was much shorter than the question. Now, we are moving on from people and things in lines to things in circles, which has an added complication. So we'll have now, for the next one, 4 people
4 whole people.
called conveniently A, B, C and D,
The parents must have hated them.
Square.
okay, are seated around a circular table.
Knights of the Round.
Indeed. How many arrangements are there?
Is it 4 factorial?
So, let's just start off by drawing 4 lovely round tables and putting on this table A, B, C, D to start with. Now, what about this seating arrangement?
That's the same thing, just rotated. So it's
Hmm.
the same arrangement.
That's the same. And so is that. And so is that. Those are exactly the same arrangements. And while we're at it, what about this one?
Yeah, same thing. Well, no,
It is
actually,
act-
it's different. Actually,
It's the same. He's sitting
It's
at
the same.
the
D.
dice.
D is opposite B and has A on one side and C on the other side.
B is in a different place.
They are on
A.
different sides, yeah. Okay, they are on different sides.
So do we count
But-
it as different or not?
That is
We are going to count those as identical here.
What?
Now, if you have a question, now you can debate here, are they the same or are they different? But if you come across a question like this, you need to really look through. So we are going to say at the moment all 8 of those are identical. Now, you need to think about maybe a scenario. So this one here going with anti-clockwise would be that, wouldn't it? So D is coming over here, isn't it? So, it's going to make my head hurt in a minute. That's right, and D we haven't got down here, have we? Okay, so there are 8. So, let's decide first of all then on our table. To start off with, we are going to seat A. Does it matter where A sits?
No.
No. So this A, the first person, and it's really important it's the first person really, A, the first person can sit anywhere. It makes no difference. If you think about it at the moment, if A sits here, you could just turn these around and you're going to get 4 the same, really. So what you are left with, the problem that you are left with, well, the problem comes down to seating the other 3 people. B, C and D. And how many ways can B, D and C be sat?
3 factorial.
3 factorial ways.
Yeah, this could be
And then if you consider clockwise and anti-clockwise seatings are the same, so we'll say here, if you consider clockwise and anti-clockwise, what do Americans call anti-clockwise?
counterclockwise.
Counterclockwise, yeah. If you consider clockwise and anti-clockwise seatings to be identical, you need to divide by 2. So, we had here for 4 people at a round table where we said clockwise and anti-clockwise we decided were the same as each other. It was 3 factorial over 2. So that does come up with the general result that if you have n people around a round table, it hasn't got to be round, it basically means the ends join up, then what will it be? Assuming that you have anti-clockwise and clockwise counted the same. So if you count clockwise and anti-clockwise as the same.
Is it n minus 1
N minus
factorial
1.
divided by 2?
It is, yes. N minus 1 factorial divided by 2. Okay, so that's a useful one to learn.
Why do we put them in brackets? Otherwise it's just 1.
Yeah, that's right. You've answered that question yourself. Fine.
By me.
Okay. Right, I think we have enough time to do a lovely little question about tulips.
First question about tulips. On the
6 tulip bulbs
6. Are you a gardener?
planted in a circle.
Circle.
Couldn't be a plant in a line.
Tulips all look the same, so it's always 1.
2 bulbs fail to grow.
I'd put buds.
What's the probability?
2 buds.
They are next to each other.
2
Ooh.
buds and 6 tulip buds.
It's like combining the last two.
Fail
Yep.
to grow.
Could you do me a favour so don't read it down?
I can move it up.
Or read it up, same thing? No, it's not the same.
Yeah. 6 tulip bulbs planted in a circle. 2 bulbs fail to grow. Poor gardener. What's the probability they are next to each other?
they can be
Big hole
placed.
in his garden.
They can be placed in different places.
Well, I'm going to suggest to start off with this, we use a G if they grew, and an F if they failed to grow.
I'm going to put failure.
And let's just have a think. We got, what have we got here? We got 4 growing, haven't we?
That's 4G.
And we want 2 failed next to each other. So we could have, for instance, that. There's my lovely circle of bulbs.
They can go in different parts of the circle.
Now, this is where you get a bit clever or crafty. What has got to be next to each other here?
The failures
Yeah.
and the G's.
Call those one thing to start with.
Very mathematical.
Call those one thing. How many things are there now in my circle?
There's 1.
Yeah, so that gives me 5 items in my circle. Those items are G, 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 FF. How many ways can 5 things be arranged in a circle? And the gardener's going to think clockwise and anti-clockwise are going to be the same.
4 factorial over 2.
Well, yeah, using this thing up here, that's going to be 4 factorial over 2,
Which is 12.
which may be 12. But what have we not yet accounted for is these 2 here.
They can be put in
They're
different places.
two flowers.
There's
Yeah,
two people.
they themselves, the 2 Fs, these 2 here can be arranged in 2 factorial ways.
So it would be 2 times 2 factorial.
So, So what we've got to do, like before, is we have got to times those things together. So we have got this over here, but then we also have to account for any position they are in. They could be arranged in 2 different ways, 2 factorial different ways, so we get that. 2 factorial is just 2. They cancel out. We are left with 4 factorial, which is
24.
24. So there are 24 ways we can get what we want to start with. But the question was asking for a probability. And the probability is equal to the restriction number over the non-restriction number. The restriction number we've just worked out to be 24. The non-restriction number,
720.
5 factorial.
6 factorial.
Sorry.
6 factorial. 1 more than
if there were no restrictions, what have we got that the gardener's planting?
6 tulips, and that's
6 tulips in a
circle.
circle.
So 5
Over 2.
Thank you.
Okay.
5 factorial over 2. Okay, that is coming from the n-1 factorial over 2 thing.
James.
That bit there is for the 6 in a circle.
60.
Okay, and that is 120 divided by 2, so that is, on the bottom, 120 divided by 2, which is 60. So we get 24 over 60, 12 over 30, 6 over 15,
3.
2 over
2 over
5.
It's quite a high chance.
Okay.
It's not. It's less than half.
And I don't think we have any more time to do any more.